we're live. All right, it's my pleasure to introduce Yerlin. He did his PhD at Columbia University and recently started a position at University of Chicago at the William H. Perskal instructor at the University of Chicago. He's done a lot of work on KPC, and his thesis is large deviations of the KPC equation, Markov duality, and SPDE limits of the vertex models. He's really an expert in this field, and I'm excited to hear him give us an introduction about to large deviation theory. Thank you, Yerlin. You're up.
Okay. Thanks, Axel, for the invitation. And today I'm going to talk something about the large deviation theory. And this talk does not need a special background in large deviation and much knowledge in probability. So I'll just assume the audience do not have much background and proceed slowly. So if you have any question during the talk, please feel free to interrupt me. So what is large deviation theory? So first, it's one of the pillars of probability theory. And roughly speaking, it concerns with the exponential decline of probability measures of certain kinds of extreme or tail events. So let's start with an example explaining what are large deviations. Consider we're tossing fair coins. So it's a fair coin, we can either get a head or a tail. And assuming that we're betting our money, so if we get a head, we earn $1. And if we get a tail, then we lose $1. So we can associate the thing with a random variable, x. So x equals 1 if we get a head, or equal -1 if we get a tail. So the probability of x to be either +1 or -1 is equal, it's 1/2. Okay. So now assume we keep betting and do this coin flipping. So we get a number of results. We get the results recorded as x1 up to xn. So there are ID random variables, each with probably one half to be 1 and probably 1/2 to be -1. And in particular, they have a name. It's called the Radmacher random variables. So we consider Sn to be their sum. So we sum x1 up to xn. So Sn will denote the net income of the betting. So we're interested in the asymptotic behavior of Sn. So the law of large number tells us if we just let Sn divided by n and take n goes to infinity, then almost surely this number will go to 0 because it's a fair coin. Okay? And moreover, the central limit theorem tells us we can also say something about the fluctuation of this number around 0. So in particular, the fluctuation is of order 1/√n. So as n becomes big, the fluctuation becomes smaller and smaller. So this number should concentrate around 0. So what does the large deviation theory studies? It studies the behavior of the probability of this number, Sn over n, to lie around some value x, where x is fixed. So as you can see, if x is not 0, then when n becomes bigger and bigger, this probability will just go to 0. Okay? So the large deviation theory cares about how fast this probability decays to 0. Okay? So for example, let's take some special value for x. When I take x to be -1, then I want to compute the probability of Sn over n to equal -1. And this just means that Sn equal -n, and it just means I should get a tail for each of the coin flipping. So each of the random variable x1 up to xn is -1. And the corresponding probability is just 1/2 to the power of n. So this probability will decay exponentially as n becomes bigger and bigger. So I'll just put everything on the exponential. So I write e to the power -n log 2. So this n really tells you the probability decays exponentially in speed n. Okay, and similar, you can also take x to be +1 and you get the same number. So what does this probability behave for general x? So for general x, let me just tell you the result. This probability will decay exponentially with speed n. So in other words, this speed n, it does not depend on where you take this x to be. It doesn't matter x is -1, -0.5, or other values. They decay in the same speed. But the rate at here, so here this function depends on x, the coefficient at here. It depends on the location of x. And it's called the rate function. And it takes this form. Okay. So in particular, I can just draw this function, something like this. It's a convex function. So actually, it's a classical theory in the large deviation theory. When you sum up ID random variable and study the large deviation of it. So this rate function actually can be obtained from the Legendre transform of the moment generating function. Sorry, the Legendre transform of log moment generating function of the Rademacher random variable.
I have a quick question, and I think this probably answers it, what you just said. But this rate function, it's model dependent, because for this you just had plus or minus, but you could do other distributions on the axis, and yes, that would change the rate function.
Yes, exactly. So the rate function, it depends on the nature of the ID random variable that we sum up. So here I put red because it corresponds to the fact that we're summing up the ID Rademacher random variables. And yeah, in particular, it can be obtained from the Legendre transform of the log moment generating function of the random variable behind. So it tells you the exact relation how you can get the rate function from the random variable.
Okay, and because as opposed to like the central limit theorem, which is kind of like a universal result, this is more model specific. Are there any universal aspects of this large deviations? Maybe the speed n?
Yeah, what is universal is the speed n. It doesn't matter. It does not depend on what kind of random variable that you're summing over. As long as there are ideas, sum them together, then this probably will just decay exponentially in speed n. But the rate function, it does depend on the nature of the random variable behind.
Okay, great, thank you.
Okay. So this actually is the large deviation principle. It's called the large deviation principle for this Sn over n, because for every value of x, I know exactly the asymptotic behavior, how this probably decay exponentially. I not only know the speed, but also know the rate. And you see here, the rate is finite when x is between -1 and 1. And this is because the possible value for Sn over n can only be taken from -1 to. Okay. So this is the first example. So now let's proceed. We still consider the example from coin flipping, and we have the same ID random variables. Now I'm interested in their running sum. So I take Sk to be the summation of this xi from 1 to k. And I'm interested in behavior of the sequence of running sum. And I encode this information into a random walk path. So it's related to something called a simple random walk. So what is simple random walk? It just means I start from 0. And at each step, I can either go up by 1 or go down by 1. Okay? So when do I go up? I go up if my corresponding random variable equal to 1. So if I get a head in the case flipping, then in the case step, I go up by 1. And if I get the tail, then I go down. So here, for example, this is a sample for the random walk path. So in the first step, it goes down, which means x1 equal -1. And in the second step, it goes up, means x2 equal to +1, and so forth. Okay. So of course, this path is also random. It depends on the result of the coin flipping. And in particular, let me say my random walk takes n steps. So in the end, it stays at Sn. So the end point position, the y coordinate of it, is exactly the random variable that we have studied in the coin flipping. So this Sn. Okay. So I'm now interested not just the endpoint position, but the behavior of this entire path, okay, this random object. So let me consider a scaling of it. So let's say I squeeze the x coordinate, squeeze the x-axis by scale n, and same for y for the y-axis. So in other words, I consider my path to be scaled to be SNT over n. So my path is just defined from 0 to 1 now. Okay? And I'm interested in the behavior of this scaled random walk path when n becomes big. So again, by the law of large number, you can show that when n become really big, this random object, this random path, will just concentrate around the constant 0 path. So here it's a simulation run. For example, take n to be large, 200. Then these paths with different colors are just different samples. You can see that they are really close from this constant 0. So it's the typical position of this random object. Okay. So then the question is, what is the large deviation theory for this random object? So in the previous example, what we studied is we just take t to be 1 and study Sn over n. But now we're interested in the large deviation theory for this entire path. Okay. Mm-hmm. So the result is, if you take a path gamma, a fixed path that starts from 0 and continuous and nice. So I don't want to explain what do I mean by nice, but you let this scaled random walk path to stay around this gamma and compute the corresponding probability. Then as n becomes big, this probability will decay also exponentially with speed n and with a rate function, depend on the position of the path. Okay? So what is this rate function? This rate function turns out to be the integration from 0 to 1. And here you take the rate function in the coin flipping example. Then you compute the derivative of your path gamma You plug in that rate function and you just integrate. So this is the rate function. So why this is the rate function? Let me just explain informally. So first you see, again, this rate function, it depends on what random variable behind in your simple random walk. So here it's the red micro random variable. Okay. So how to see why this rate function is an integral? Actually, you can look at this event. This event tells you my random walk path to stay around this gamma. And I can just divide my time interval 0, 1 into m equal pieces. And I consider the endpoint of these pieces, Ci, to be I over m, where I is from 1 to up to m. Then I can approximate this event by the endpoint position of the pieces. So I can approximate this by the probability of Sn Ti over n stay around gamma Ti, and you let I to be 1 to up to n. Okay, so this is a discrete approximation. And in the end, we're going to take m to be really big. And then this tells you the position of the intermediate point in your random walk. And you can actually compute, transform this event into the random walk increment from I from 1 to m, and then use, because the increment of the random walk, they're independent with each other, so you can just compute each probability, I mean for each I respectively, and multiply them together. Then when you compute this event, the probability of this event for each I, you can use the large deviation principle that we obtained in the previous example. So let me just tell you what does this probability behave asymptotically. It will just behave as exponential of minus n, and you sum over things from 1 to m, and now this rate function appear because we use the large deviation principle for the coin flipping. And now you consider this increment of the gamma path, then you divide things by 1 over m. So this is an approximation for the probability on the left hand side. But when you let m goes to infinity, first this term, it's exactly approximates the derivative of gamma, because when you take m becomes bigger and bigger, it's just a discrete version of the derivative. And sorry, here forget 1 over m. And this summation, you would approximate a Riemann sum of the integral at here, because I divide things in pieces by 1 over m, and I sum over these values. Okay, so this is why at here, when you look at the large deviation theory for the random walk path, you will take the form of the integral of where you integrate the rate function in the previous example. Okay, so is this does this informal explanation make sense?
Yeah, thanks.
Okay, great. So this is another example. It's a second example in this talk, and I explain the large deviation theory for the simple random walk. Okay. So now there's another important concept for the talk. It's called the most probable shape. So remember, if we're just interested in the law of large number for this random path, it will concentrate around zero, or just concentrate around the constant zero path. But now, if I do some conditioning, so let's say now I know, or I only look at the random walk path such that the endpoint Sn, or look at Sn over n, is equal to x for some fixed x. Okay, so condition on this event, I want to understand what is the typical position, or it's called the most probable shape of my random walk path as n goes to infinity. Okay, so mathematically it just means I condition on this event, and I want to find a path gamma, a deterministic path, such that my random walk will stay around my gamma, arbitrarily close as n goes to infinity. Okay. So intuitively, if we just use nothing from probability theory, but just our intuition, what should the most probable shape be if I do this condition? So it's something like, if I do no conditioning, then the most probable shape is that here. But now I say I only consider the path such that my Sn over n is x. So I only want my path to end at location x. Then my path should really just concentrate around the straight line from 0 to x. It's like I force the endpoint of my string to be away from 0, then the behavior, I mean, the position that concentrates should just be the straight line from 0 to from the origin to 1x. So indeed, as you can see from the simulation, if I only sample my random walk so that its endpoint lies around, for example, 0.5 n, and I take n to be large, then you can see the scaled random walk path is Sn over n. So these paths with different colors denotes the different sampling. It will concentrate around this straight line, which represents y equal to 0.5 times x. This black line. Okay. But how to understand this intuition mathematically? So actually, it used the large deviation theory for the simple random walk that we just explained. So if we condition the endpoint Sn over n to be x, then every path here with the endpoint Sn over x equal to Sn over n equal to x is unlikely. Okay, we take x to be not 0, because a typical path will just have Sn over n goes to 0, but we do this conditioning, so we only look at paths with endpoint deviate from 0, which means every path is unlikely. Okay. So what does the most probable shape corresponds to? It corresponds to the most likely path among all the unlikely paths. Okay. So what does unlikely mean? The unlikely mean is every path gamma. We look at every path gamma at here. As long as the endpoint is not 0, you will have some exponential decay. I mean the probability here will just decay exponentially. So this is unlikely means. Sorry, I'm rolling a bit fast. And what does the most likely mean? The most likely means, although every path, I mean, when you look at the probability lying around it, have an exponential decay, but I'm looking at the paths that have the smallest rate of decay. So for each gamma, I will have a rate function, okay, which if the rate function is bigger, it means the decay is faster. So I want to look at the gamma that satisfy this endpoint conditioning. This corresponds to Sn over n equal to x, such that the rate function is smallest. Okay, so the most probable shape, from the large deviation theory, actually tells you should be the path gamma, which minimizes the rate function for the simple random walk, given this endpoint conditioning of my random walk. Okay, so then the problem just becomes finding the minimizer of a variational problem. So I consider all the paths start from 0 and end at x, and I want to minimize this integration. Okay, and then you can actually using the convexity, the rate function of the red macrorandom variable is convex, you can show. Then using convexity, actually, we can show that the minimizer should have constant derivative, so it should be a straight line. Okay, so this is actually a proof for why the most probable shape at here, the gamma star at here, should be a straight line connecting the origin and 1x. Okay, so does this part make sense, for example?
Yes, I just have a quick question, and I assume that you can fix other points in the path and the story would generalize by minimizing the rate function, so you can condition on other points. Is that true?
Yeah, that's true. You can also just condition some intermediate points such that yeah, can also study the most probable shape. Conditioning, for example, Sn over 2 over n equal to y. You can also give some more conditioning. For example, I do not just only condition the endpoint, but also condition some intermediate points. And the logic is similar. The only thing that you're doing is from the large deviation principle, you just give an extra condition at the here, which is corresponds to this condition, and you want to minimize the rate function given this condition. The minimizer is the most probable shape.
Okay, great, thanks.
And it will be piecewise linear.
Yes, exactly.
And it doesn't depend on it's the result. All you need is IIT. Excellent. They don't have to take like two values, right? So they could be like, could this be like continuous?
Right. The only thing that, yes, you're right. The only thing that I use here is the rate function here is convex.
Right.
Yeah.
So yeah, that would be like piecewise straight path in area too.
Right. That's true. Yeah. As you can see in the next example, where I will also consider the most probable shape for a continuous object. So yeah, now I'm going to talk about the Brownian motion. And the Brownian motion, I'm going to define it just, still I look at this simple random walk. I still look at this simple random walk, and I consider different scaling as the case I look at large deviation principle. So I just divide things by root k. Okay, and I take k goes to infinity, then
comment.
There's a comment. Okay.
No, sorry. Yeah, Ed Waymeyer just made a comment that you assume finite.
Yes, that's true.
Yeah, so go ahead.
Yeah, so the Brownian motion can be just viewed as a scaling limit for the random walk path. When you take this k goes to infinity. Okay, and it's something you can see from the picture. It's something that is it is pretty rough and it is not differentiable. So I just do this simulation. Sorry, simulation. When k is really big, it's an approximation of the Brownian. So the Brownian motion is very important, and it's a fundamental object in probability theory, and it models the motion of pollen particles as being moved by the water molecules. And it has the following properties. Actually, the only property I'm going to use here, so of course it starts from 0, and you can also see these properties. It just inherits from the random walk. It has stationary and independent increments, and this is by central limit theorem. It has a Gaussian nature, so the increment of it has a normal distribution with no mean and variance. And also, because it's a scaling limit of some object of the simple random walk, then it has the scaling variance property, which means the process BNT has the same law as root n times b. Okay, so now I want to study the large deviation principle for the Brownian motion. So similar to the simple random walk, I also consider this scaling, okay, because the Brownian motion itself, it can be viewed as a continuous version for the random walk. And so now I'm going to take a slightly different form of it. So because the Brownian motion has a scaling property, so the law of this random path, it has the same law with this quantity. So I do not need to scale the time anymore. I only need to multiply by root epsilon, where epsilon is equal to 1 over n. Okay, so it's the same as looking at this quantity, which again, these two objects has the same. So I'll just stick on this notation. So I'll just stick on this notation afterwards. So again, I look at the probability of the Brownian motion to stay around a path gamma. Okay, and there's also a large deviation principle for it, and this probability will decay exponentially with speed. Now it's epsilon to the power -1, but it's just the same as n that you see before, and with a rate function. Okay, so this Bm denotes is the rate function for the Brownian motion, and it takes a similar form actually, as you see from the simple random walk. It's also an integral. So it's an integral from 0 to 1 over 2 gamma dot square. So it's actually also, it can also be written in the form as something like the integration of 0 to 1 I gamma dot s ds. But now this I is given by 1 over 2 x squared. Again, the form of this function is different from the previous example in the simple random walk, and it depends on the nature of the random variable behind. So here, the form depends on the Gaussian nature. Okay. So once we have the large deviation of Brownian motion, so it's now a continuous object, we can also study the most probable shape. So for example, I condition my endpoint. Sorry, here actually it should be. I'll just stick on the notation to be root epsilon. Okay, so I condition my endpoint to be y, and I want to understand the most probable shape for my path, root epsilon b. Okay, as epsilon goes to 0. So again, what is the most probable shape? Now I'm just going to explain it from the large deviation theory. So the most probable shape should just be the minimizer we want to minimize the rate function for the large deviation principle of the Brownian motion, given that my path start from 0 and end at y. Okay, so this condition corresponds to I condition my endpoint of my Brownian motion, the scaled Brownian motion, to be at 1. And sorry, there's some typo. So we want to minimize actually this quantity given the starting point and ending point. And the minimizer should just have should have a constant derivative. So the minimizer should be a straight line. So it means that given that my Brownian motion, the scaled Brownian motion at time 1 is at location y, the most probable shape of my Brownian motion as epsilon goes to 0 will just concentrate around this straight line. Okay. So this is just follow from the same logic as what we do from the simple random walk, from the example of the simple random walk. Okay, so does this make sense?
Yes.
Yep.
Okay. Now I'm going to talk about something that is related to the stochastic differential equation or stochastic PD. So I'm not going to talk about the equation, but I'm going to talk about something called the spatial white noise and the space-time white noise. So let's first talk about the spatial white noise. So what does it mean? It just means we take our Brownian motion from the previous example, and the white noise is just the derivative of it. Okay, but be careful. The Brownian motion itself is not differentiable. Okay, it's not differentiable. So this means the white noise, disk C, is not a pointwisely well-defined function. So if you just want to visualize it, so I do a very rough simulation of it. You can see it's something that is oscillating so quickly, so that the white noise cannot be pointwisely it's not pointwisely well defined. Okay, so the way to define it is to define it as a generalized function. So what does a generalized function mean? It just means we consider a test function, a compactly supported and smooth test function G, and I integrate it against the white noise, and I define this to be the way of integration by parts. Okay. So for those who are familiar with stochastic integral, it's also the same as I integrate my G against the Brownian motion, dBt. And the integration is understood in the Ito sense. Okay. So informally, you can also understand the spatial white noise as a Gaussian process with the correlation function to be this Dirac delta function. So what does this mean? It just means that you consider test function f, which is compactly supported and smooth. You integrate against the white noise. Then this, as a family of f, you take different test function. It's a Gaussian field. And you can also compute the covariance function for different test function. To be the integration of f times t. So this is what I mean by their correlation function is Dirac delta. Okay, so now I'm going to study the large deviation principle for the spatial white noise. And I'm going to first tell you the result and explain it again informally. So the large deviation of the spatial white noise corresponds to, I scale it by root epsilon, and that epsilon goes to 0. So typically, this quantity, you'll just convert to 0, right? But I want to understand the probability of it to stay around some L2 function rho. Okay, and this probability turns out to decay exponentially with the rate function actually given by this 1/2 times this integral, the square of the L2 norm of rho. Okay, so why is this true, or where does this come from? So informally, you can think of it this way. When you look at the probability of the white noise to stay around my my L2 function, remember the white noise is the derivative of the Brownian motion. So it's the same as looking at the probability of the derivative of Brownian motion to lie around my rho. Then you can say, okay, it should be similar to look at that my Brownian motion to stay around the integral of my rho. Okay. Then because we know what is the large deviation, principle for the Brownian motion, then you can just plug in the rate function that we see before, which is the derivative of this integral, and then you integrate again, where it at here, and 1/2. So to just plug in the rate function of the Brownian motion, and you'll see this result. Okay. So this is the large deviation principle for the spatial white noise. And you can also study a similar object, study the large deviation principle of it. It's called the space-time white noise. So it's just a 2-variable version of the spatial white noise. It's again, you can informally understand as a Gaussian process with the correlation function to be both direct delta in space and time. And you can also, similar to the spatial white noise, which can be defined as the derivative of the Brownian motion, the space-time white noise can also be defined as a space-time derivative of a 2-variable version of the Brownian motion called the Brownian. Okay, so in the end, I'm just going to state the large deviation principle for the space-time white noise. It's similar to the spatial white noise, where you look at the probability of root epsilon, C to stay around my L2 function rho, and it will decay exponentially with speed 1/epsilon and the rate function to be the L2 norm as epsilon goes to 0. So why I'm explaining the large deviation theory for the white noise, because when you look at the stochastic differential equation or stochastic PDE, they're usually driven by some random thing called noise. So when you want to study the large deviation theory for the stochastic PDE, a very important ingredient is to first understand the large deviation for the driving noise behind, which can help you a lot when you want to derive the large deviation principle for this stochastic PDE. Okay, so I'm going to stop here, and feel free to ask any questions. Thank you.
All right, we have some time for questions. I open the floor for questions. from the room or the chat? All right, I have a question. So for this SPDE story, so if you have a random variable that's defined via an SPDE, and then you do this large deviation theory principle, and as you did for the coin flipping, you then had a minimizing problem, and you got straight lines. And for the SPDE story, are we expected to obtain a PDE problem from the minimizer problem? Is that how?
Yes.
Is that how it typically happens?
Yes. So when we look at stochastic PDE, for example, let me just write down some stochastic PDE, the KPZ equation. So again, my solution is called H epsilon. It will depends on this coefficient out here, and I have a large deviation principle for the space-time white noise. So actually, we can also in the end we're going to prove a large deviation principle for H epsilon. But for the most probable shape, if you just do no conditioning, you let epsilon goes to 0, then my solution H epsilon will just converge to the shape where you which is a solution to the PD at here. You just surround the white noise because you let epsilon goes to 0. This noise disappears. Sorry. And if you do the conditioning, for example, you condition up the 1 point value of my solution to be a given value, then things will change.
Would this become boundary conditions?
Yes, this will become some boundary condition, and things will become more complicated than in the case you just do no conditioning, where you will get some different PDE behind. Oh,
so the PDE is going to be more complicated than just dropping the noise and adding initial conditions or at boundary conditions?
Yes, because for example, my KPZ equation it already starts from some initial condition. So if you just drop this noise term, then I mean you just get a shape. But now if I want to force my solution, let's say at time 2 and position 0 to be very far away from the typical shape, then this noise in the end will not vanish anymore. You'll converge to some also there's also some shape for the noise, and my solution the most probable shape will be the solution to the PDE where you plug in the most probable shape for the noise actually. And it's very important to understand what is the most probable shape of the noise if you do some forcing of my of the 1 point value for my solution.
Okay, thanks.
I have like a broader question about large deviation theory, and I'm kind of thinking about like data assimilation or data analysis, where maybe you have some PDE or a model with like an SPE, and you have freedom in parameters of that model as well. Is there any connection with like trying to use large deviation theory in that context? And maybe you don't know this, but I'm just curious.
Yeah, I'm not so sure, to be honest, because I'm not really an expert in the data analysis. Yeah, probably there's some interesting application from the large deviation theory. Yes.
Yeah, it's super cool. I really liked your talk. It was very clear, and it just got me thinking about about that, which is something I think about on my own.
Yeah, it's definitely an interesting thing to. I mean, it will be great to connect the large deviation theory and see some application of it in the data science. Yes, thank you.
And from what I understand is parameter fitting. That's the basic
Yeah,
question.
and I mean, here you have like parameter fitting along with you have noise and like the data, and so you want to fit to these time points.
I see.
Cool, thanks.
Any other questions? I had a quick last question. For the rate function, you mentioned that this is determined using the Legendre transform. So
Yes.
Is it correct to think of the rate functions as some sort of energy function? Does it have a physical interpretation that way?
Yes.
Okay.
Yeah. I think it's correct to. I mean, if you think physically to understand the rate function as the energy function, because where does the law of large number hold? The law of large number holds where you at the position you minimize the rate function.
Okay. Yeah, I just wanted to clarify that. Thank you. Yeah. If there's no more question, let's. What's that?
Questions online.
Questions online? I'm not sure if I saw.